Okay, so here's the coming week. We're starting chapter 15, which is called multiple integration or double integration or something like that. I know I should know that, right? And this is the week ahead. We're going to try to do 3 sections. The web work is all there and ready to go. I've got some supplemental material on the right-hand side there. Double integrals and polar coordinates are both videos, actually several videos from the Khan Academy. So if you're looking for a different perspective on the material, you can watch those videos. And then I've also got this region sketcher thingamabob up here, which we'll use later in today's lesson and a little bit on Wednesday as well. This will help you practice a little bit with the algebra of computing limits of integration, which is really going to be the big skill set that we're trying to develop here in the next couple of days. Okay, so what's going on here with chapter 15, and let's step back a little bit and think about more generally what's going on. I know it's been a while since the beginning of the semester, but one of the things I mentioned at the beginning of the semester was that the arc of Calc 3 in some ways parallels Calc 1 and Calc 2. And if you think back in Calc 1, you learned a little bit about functions, and then you went into differentiation and applications of differentiation. And then in Calc 2, you learned about integration, and not really at the end, but somewhere in the middle, kind of, you learned about the connection between integration and differentiation. And in fact, that connection, called the fundamental theorem of calculus, really formed the foundation for a lot of the rest of Calc 2, that being techniques of integration, finding antiderivatives, plugging in limits, etc. What you're seeing here in Calc 3, we spent a little bit of time on preliminary stuff, vector functions, vectors, planes, lines, etc. Then we spent chapter 14 doing differentiation, which is sort of like Calc 1. And now we're moving into integration. How do you integrate functions of several variables, and what do those integrals actually represent? That's where we're headed now. And then we'll finish the semester, chapter 16, with some of the most beautiful theorems that exist in mathematics, namely Stokes' theorem, the divergence theorem, and Green's theorem, not necessarily in that order, where these things connect the ideas of partial differentiation on the one hand and multiple integration on the other hand, in the same way that the fundamental theorem of calculus did connect regular differentiation and just regular integration. And what you're going to find, actually, if you're really astute, and I'll make sure that I point it out, is that the divergence theorem is really just a generalization of integration by parts, and really is sort of an elevation of the fundamental theorem of calculus. So, without further ado, let's talk a little bit about multiple integration. So section 15.1 is laying the groundwork for just multiple integration. And if you want, it's not a phrase that the book uses, but if you want, you can think of multiple integration as really partial integration as a contrast or a counterpoint to partial differentiation. That's kind of going to be what guides us through these calculations. Some of the skills that we're going to be drawing on, you need to, if you don't sort of have firmly ingrained in your head the equations of circles, the equations of ellipses, the equations of lines, the equations of parabolas, all those fundamental basic curves, if you don't have that stuff really automatic, that's where you'll be at the end of this chapter, because you're going to be sketching regions bounded by a parabola and a line, or bounded by a circle and the x-axis, or what have you. You're going to have to be identifying these regions that are bounded by curves that you're familiar with. And in order to do these multiple integration problems, you need to be able to sketch out these regions that are bounded by curves pretty quickly. All right, so I'm going to switch over, I think, to the notebook here and start with an example from Calc 2. Do you remember volumes of revolution? Slightly ring a bell? So the idea that we're going to use to build these multiple integrals is somewhat related to the ideas that were found in computing volumes of revolution. Okay, so let's go and look at a volume of revolution. Just the simplest possible case. We don't need to revisit the whole messy topic. Just the simplest possible case where you have a nice function above the x-axis. Oops, maybe a little too far above. Between A and B. Right, and if you go around the x-axis, what you get are things like that, right? So does that ring a bell a little bit? And I don't know if you guys did it in your Calc 2, but the derivation of the formula to compute this volume of revolution, that derivation used an idea that we're going to be using today. And that's why I think it's worth starting here. The way this worked is you picked a value of x between A and B, and you looked at a slice. And what we did in that is in this example is we computed the area of that slice. So the area of the slice at x, which will denote capital A of x. What kind of shape is that? It's a circle. And what's the formula for the area of a circle? Pi r squared. And we happen to know what the radius of that circle is, right? F of x. F of x. So the area of that slice is pi times f of x squared. And then I don't know how your instructor may have done this, but what I'm going to do is I'm going to fatten this guy up a little bit. And I'm going to give that guy a width, dx. So I'm going to fatten this thing up in the x direction. So what I have now is essentially a cylinder, very much like a coin. And how do you compute the area of or the volume of a cylinder? What's the general approach for the volume of a right cylinder?
Or the area of the circle times the width.
So more generally, the area of the base times the height, right? Area of the base times the height gives you the volume of a cylinder. And that way we can have not just circular base cylinders, but any kind of sort of crazy shape on the base, multiply by the height, and you get the volume. So that's all good, right? Okay. So what I'm going to do is fatten this thing up just a little bit by an infinitesimal width. And I'm going to call that dV. So this little slice of volume, I'm going to denote dV. Once I know the volume of this little dV, this little slice, I can actually calculate the volume of the entire figure by using what tool? I can integrate, right? I can integrate, I can sum up all of these infinitesimal slices, starting where? Starting at A, there's a slice at A, and taking all the slices all the way up to B. And we get the volume of the entire figure. All right, this idea of taking slices, little slices of volume, and adding them up is the foundation of multiple integration. And so what I want to do now is leave Calc 2 and leave volumes of revolution and take this idea and apply it to a more general kind of volume. And let's see how good my artwork is here. Okay, so here's some surface. Not good. Let's go here. There we go. Let's take some surface. And in this class, we've been describing surfaces by functions f of xy. Z is equal to f of xy, right? And let's put some bounds on in the x direction here. This is x. This is the y direction back here. This is z. And let's put some bounds in place here. Let's call this A in the x direction. Let's call this B in the x direction. Let's call this C right here. And back here we'll call that D. If I were to look down upon this thing, I would see A, B here in the x direction, C, D here. Okay, you know that's what I like to do, right? I like to come out here and stand on the xy plane, and I like to look up at the surface above me. Okay, and that's the picture that I want you to get in your head. Okay, I would like, does everybody see how the space underneath the surface and above the xy plane is actually a volume? It's kind of like a loaf of bread, sort of nice flat on the sides and then wavy on the top in this particular case? Okay. Maybe a brownie pan or something, perhaps slightly more interesting. That idea of taking a slice and summing it up, we can use that idea here to compute this volume. Go ahead.
I guess the only thing I'm confused about is that it looks like it's flush with the y-axis on the top, and then on the bottom it looks like there's some distance.
I just, yes.
So should it be off the y-axis a little bit?
Yeah, I was just trying to be a little bit more general down here,
Okay,
so
gotcha.
yeah, it's unfortunate, I suppose. I can't fix it at this point.
It's okay.
I might be able to fix it. There. Okay. I guess the thing I'd like to point out to everyone is it's not necessary that this region abut either of the axes. It can just sort of float out there in the middle of space, and it can be off either one of the axes. What I'd like to do here is, following that same technique, I'd like to pick an x value here and look at a slice. Okay, that slice up on the surface actually traces out some, I don't like that. It's close, but here maybe, here. Okay. So that slice, that fixed value of x, gives me a slice of the brownie. I like the brownie. Okay. Now if I were to take that and go and look at the xy axis, so let's take this guy out. I'm sorry, the YZ axis. And then here's C, here's D, and here's the curve up above. So do you see what I've done? I've taken this guy and I'm looking at it from the side now. This curve up here, this curve is just f of x, y, where x is some fixed value and y is allowed to range between c and d. X is a fixed value and y ranges from c to d. So that's what this guy is. Back to Calc 2, how do I find the area under that curve? I just integrate, right? Now x is fixed, so which variable am I integrating with respect to? Y. Partial integration. So the area of this guy is the integral from c to d f of x, y, dy. So the area of the little red cross section is given by that formula. What's the next step? If I want the volume of the entire figure, what's the next step? Fatten it up by a dx. So let's do that. I'm going to sketch that in right here. So we'll fatten that up by a dx. And so dv is just this area of the cross section times dx. Now, over what range of x values am I building these cross sections? Remember, x was an arbitrary value between a and b. So if I would like to get the volume of the full brownie, what's the next step? Integrate with respect to x from a to b. So the full volume, let's go back to black here. The full volume is given by what's called a multiple integral, or a double integral. And the way that you do this is you evaluate this integral you evaluate the inside, treating x as a constant, and then you integrate the rest and then integrate with respect to x.
And it doesn't matter which order you do.
Well, God, we would hope not, right?
Yeah.
Yeah, because whether I do slices with a fixed x and then sum them up, or I do slices with a fixed y and then sum them up, it's still sweeping out the same volume. That's something to be proven, however, and it's not something that we prove in this class. It would be more of an advanced calculus class. But the theorem is actually mentioned in the book. It's called Fubini's theorem. So Fubini's theorem is sort of Clairaut's theorem for integration. Okay, remember Clairaut's theorem said that it didn't matter whether you differentiate with respect to x and then y or y and then x. Fubini says the same thing. It doesn't matter whether you integrate with respect to x and then y or y and then x. And I think I will just leave, this picture is almost a proof. Right? Doing it, fixing an x and then integrating, fixing a y and then integrating. It's the same volume. That's as good a proof as me putting up pages and pages of symbols in front of you. It's probably better. Henry, did you have a question?
So, if we were to like apply this to the very first thing about the revolution, volume of revolution, we could do that by integrating to find the surface, or to find the area of the circle, and then integrating again.
There's a problem with this surface, Henry, that makes it hard to apply the method that I just derived. And that's the fact that this surface is not the graph of a function.
Right.
And so you can't really apply this approach. You can, but it's more work. And you can find equivalents. But what you have to do is find an equation for the upper surface and an equation for the lower surface, and then top minus bottom, and then integrate over. There's probably some sort of funky region of integration down in here.
Would it wouldn't just be one line revolving to create the same surface?
Yeah, I'm not like right now totally connecting with the idea that you have in your head, but suffice to say, there probably are other ways of doing this. Here's one way, but what you can't do is this, because the surface is not represented by z equals f of x, y. Okay? But bear with me as we go through today's topic, and I think you may start to see some alternatives. This seems very limited right now, but as we go through the lesson, I think you'll see that there's a lot of power here to just considering z equals f of x, y. All right, so integrate with, where are we? Let's do an example, an explicit example. A blessed explicit example. All right. So let's find the volume under the paraboloid above the region. I'm going to introduce some notation. I think I've used this notation in here before, but it's going to come up a little bit more often now. Find the volume under the paraboloid above the region -1 to 1 cross -1 to 1. Does anybody know what that represents geometrically? Andy?
Just a box on the actual.
It's a box, and it's actually a square. And in the x direction, it's a square from -1 to 1, and in the y direction, it's from -1 to 1. So let me sketch that for you. And this is just a shorthand way of expressing those kinds of figures. All right. So what does it mean? It means take the interval from -1 to 1 and sort of glue it together, or cross it with this other interval from -1 in this direction. And together they make up this region. And it's not just for perfect squares. I mean, this could be 0 to 2, and then minus 1 to 1, and that would be a different rectangle. But does everybody see how it works? And we always assume that the first guy is for the x values, and the second guy is for y values. It's consistent with the ordered pair x, y. Right? So the first coordinate comes from the first interval. The second coordinate comes from the second interval. Okay. We want to find the volume under the paraboloid above this region. So here I am out in the region, and above me is the paraboloid, although I use the word above loosely because, in fact, this paraboloid actually comes down and touches the xy plane where? At the origin. And then everywhere else it lifts up and away. So it's kind of a bowl-shaped figure. All right. Does everybody, can you kind of imagine that there's this volume underneath the surface and above the xy plane? Okay, so let's try to find that volume. So, we have this volume integral, which I just described. When I write it in this way, what it means is x is a constant. On the inside integral, x is a constant, and we're integrating with respect to y. Once we figure out what that result is, then we integrate the rest. We integrate with respect to x. Work from the inside out. So that means, and you have to be organized when you're doing these problems for homework, right? Don't be afraid to just extract a piece of the integral and work on it. Don't try to keep it in situ and work on it there, because you're gonna risk making a mistake because you're carrying around all these unnecessary symbols. Pull this guy out and just work on it by itself. Now remember how this works? X is some fixed constant. So we're integrating with respect to y. Does everybody see where that came from? If I integrate a constant with respect to y, don't I just get the constant times y? Yeah. And then y squared just integrates to 1/3 y cubed. All right, now we plug in 1. And we plug in -1. And subtract. A little bit of integration review. It's been a while. Plus 2/3? Plus 2/3, yes. So that inner integral works out to 2x squared plus 2/3. But I'm not done. So that's sort of an aside. Now go and put that thing back from where it came from whence it came, 2x squared plus 2/3 dx. And now you have another Calc 1 problem. So let's do that guy. Two-thirds x cubed plus 2/3 x. Everybody agree with that? All right. Looks like 4/3 plus 4/3, 8/3. So the volume under the paraboloid above the xy plane in this region is 8/3, whatever that means. This is not the most enlightening kind of exercise, but it's where we are. It's where we have to start. These integrals and these processes are important. For example, when you start doing electricity and magnetism in physics, and you start looking at, how much electric field is going across a particular surface, that becomes important. These kinds of integrals become important. If you're in chemistry and you're interested in sort of reaction diffusion equations, you know, you've got some reaction going on in a vat of liquid, and there's diffusion going on and all that kind of stuff. Again, you might want to know how the different chemical species are floating around in your solution or what have you. So this is all, we're not teaching you this math just because it's pretty. We're also teaching it to you because it's useful. All right. But again, we've got to start somewhere. All right, let's step up a little bit here and talk about non-rectangular regions of integration. So the initial derivation that I went through was over a rectangular region, and this example that I just did was over a rectangular region. But in fact, that's in no way is that a requirement. That idea of taking slices and then summing up slices, you don't have to have a rectangular region in order to do that. And so let's look at that by example. Let's find the volume, or let's write an integral under f of xy, for the volume under f of xy, above the region bounded by, and here comes a long list of stuff, x equals 0, and you may have seen lists like this before, y equals 0, y equals 1 minus x. Have you ever seen a list of stuff like that before? Does it evoke a certain kind of problem from Calc 2? Remember when you're trying to find the areas bounded by some curves? Okay, all of those skills that you developed doing those kinds of exercises are now back in play. If you don't remember a lot of that, or you want to review, go pull out a calc book and just look at that section about area between curves. Okay, or pull out your own calc book. It's in there as well. Write an integral for the volume under f of xy above the region bounded by the curves x equals 0, y equals 0, and y equals 1 minus x. I'm not giving you an explicit f, because what I want to do, what I want to focus on is the region and not the actual f that we're integrating. So to do this problem, you have to sketch the region. So when you're sketching regions, you're primarily, in fact, you're always concerned with the xy plane. And let's drop these guys in here. X equals 0 is the y-axis, right? And y equals 0 is just the x-axis. The last constraint, y equals 1 minus x, what's that? It's a line. Slope? Y-intercept? 1. So something right, I'll try to draw it nice and big here. So 1, 2, 3, 4, here, say, and that's right through here. So the region of integration is that triangle. We don't know what f is, but presumably there's some surface up above, right? And so you've got some space between the surface and this triangle, and we're trying to figure out what's the volume of that space. You can fix an x, you can fix a y. Let's fix an x. Let's do both. So fix an x first. Okay, so I'm interested in the area of this slice. What slice? Well, remember, there's a surface up here, and when I fix x, there's this slice up here to the surface. So I fix an x, that means I'm going to integrate with respect to y first. I'm going to integrate along the y direction first. So that means I need to form limits of integration. Let's go back to black. I need to form limits of integration with respect to the y variable. When I start down here, what's the y value? 0. And no matter where the slice is, it always starts at 0, right? So when I'm integrating along y, one of these cross sections, I always start at y equals 0. And then I go up to, now that's the question. I go up to what? What does y equal at the top? 1 minus x, right? How far up I go depends on where I place the slice. So it depends on x. But once you figure that out, the integral is going to take care of the rest for you, thankfully. So in the y direction, I always start at 0. I always end up at 1 minus x. And then often these outer limits are a little bit easier. The outer limits are really just describing where the slices exist. So where is the leftmost slice located? X equals 0. And where is the rightmost slice located? X equals 1. That's the volume integral. Now, as Ethan mentioned, and probably several others of you have thought, there's no real preference for fixing x and then doing x first and then y, or sorry, doing y first and then x. So let's flip this around and look at, let's see if we can do the same integral where we fix a y and we integrate with respect to x first. So if we're going to integrate with respect to x first, then we rewrite the integral and look at the notation. The order of these little dx dy's changes to indicate that we're going along the x direction first and then along the y direction. It's very important that you pay attention to the order here because that sort of controls the order here and the order of integration. Okay, let's look at this slice. We're integrating in the x direction. When we're here, x is what? 0, good. And when we're here, x is what? How did you figure that out? Yeah, and that's something that you have to get used to. It's somewhat of an unfortunate example that when I solve for x, I get pretty much the same formula. X equals 1 minus y. That's okay, we can deal, we're all adults here. So x is equal to 1 minus y. That's the curve, right? Okay, over what range of y values do these slices exist? What's the lowermost slice? 0. And the uppermost slice is y equals 1. This is called reversing the order of integration. It's a really powerful tool to be able to do this. It's a skill that you'll be developing over the next couple of days. And these integrals are equal. And that's Fubini's theorem. I wish I could tell you to reverse the order of integration to just, oh, you can, swap these and swap this and change the sign over here and it would all work out. You can't do that. To reverse the order of integration it always requires a sketch of the region and a really careful understanding of the curves that are bounding the region. This guy so happens to resemble this guy quite a lot, but it's just happenstance. Sometimes you reverse the order of integration and the limits look totally different. Totally different. All right, let's look at another example here. So like I said, sometimes changing the order of integration can take an impossible problem and turn it into an easy problem. So let's look at that. So now I don't really care where this integral came from, but now it's sort of sitting in front of me, and I have to calculate it. Okay, so you remember my advice to you. In fact, it's more than just advice, it's a requirement that you start with the inside integral, you evaluate it, and then you do the outside integral. Okay, the inside integral says we need to integrate with respect to x first. Unfortunately, sine x over x is not a function that you have any ability to find an antiderivative for. You could start hacking away at it with integration by parts, what have you. You're not going to get anywhere. So sine x over x is a hard function to integrate. So it's hard to find an antiderivative for sine x over x. Let's try reversing the order of integration. Okay, in order to do that, we need to sketch the region. Okay, so let's do that. Down here in the xy plane again, where we like to walk around. Okay, x, y. Okay, let's think about what this integral is doing, even though we can't evaluate it. We're integrating with respect to x, so we're integrating parallel to the x direction first. And x starts out at y over 2. It starts out at the curve x equals y over 2. I don't know about you, but I'm more comfortable thinking about y equals something of x. So I'm going to just sketch this curve in a way that I'm more comfortable with, y equals 2x. So if I do that, something like this. There's y equals 2x. Okay, and then it starts at x equals y over 2 and it ends at x equals pi over 2. Where's that? What is that curve?
I mean, it's a line.
It's just a vertical line at around 1.5, right. So let's sketch that in there. I'm just going to sort of arbitrarily slap it right in here. Okay, and what we see is some kind of slice like that, right? We start at y over 2 and we end up at pi over 2. Does everybody see that? Okay, now, the slices go from where to where? 0 to pi. Where do you think pi is in this picture? We know where 0 is. Pi is, it actually happens to be right up here. That's not really an accident. So there's pi up there. So the region of integration is this triangle. We have a pretty good grip now on this region of integration. We know where all the bounding curves are. We understand how this integral is being executed. What we want to do now is flip things around. So we'd like to integrate, and I'll give myself a lot of space here. We'd like to do dy dx, right? Instead of dx dy. So dy means that I'm going to integrate parallel to the y-axis first. So I'm going to fix an x, and I'm going to integrate parallel to the y-axis. If I do that for this slice, where does x start? And where does it end up? Y over 2?
Starts at 0. Goes on the x-axis to pi over 2.
I'm looking at the red one.
Oh, how high it is.
So in here, y is what?
0.
And here, y is 2x. I should switch back to black here. So does everybody see that? That's really important. For a fixed x, what's the y value here? It's 0. What's the y value here? 2x. Okay. Over what range of x values do these red slices exist? 0 to pi over 2? The leftmost slice is at 0, the rightmost slice is at pi over 2? Okay. The integrand stays the same, sine x over x. That doesn't change. The limits change, and the order dx dy changes to dy dx. And Fubini's theorem says this is going to be the same number. Does everybody see why this is at least slightly advantageous? Yeah, because now when I integrate with respect to y, always work from the inside out. I'm integrating sine x over x, which with respect to y is just a constant. So let's go over here aside. Oops, not pi, x. All right. And yeah, all I do is throw in a y. No work at all. And what's really nice is when I plug in these limits of integration, the 2x actually gets rid of the problem that I was having. And the inner integral is just 2 sine x. Let's finish the outer integral. Now we suddenly have an integral that we can do. We plug in pi over 2. Cosine of pi over 2 is 0. Minus cosine of 0, 1, so minus a negative 2. and we get 2. So the area under this curve, whatever it is, don't really care what it looks like, is 2. Notice I really don't care what this looks like in this particular case. What I really care about is the region of integration. Questions about that? All right, I have a nice applet online here that I mentioned at the beginning of class called Region Sketcher. I'm going to switch back over to laptop mode here and show you how this thing works. It's a little Flash applet, so you have to make sure that you have Flash installed and enabled. So here's exactly the scenarios that we've been talking about. We've got this integral f of x, y, dx, dy. We've got limits of integration that we can fill in, and if we fill things in, we fill these things in, then the applet will give us a sketch of what's going on, whether you're doing slices, horizontal slices or vertical slices or what have you. Let's look at these limits of integration. They're a little bit truncated here, but first of all, we're integrating with respect to x, and so that means horizontal slices, parallel to the x-axis. The lower limit of integration is y squared, and the upper limit of integration is y on the inner integral. That means that x starts out at y squared, and it ends up at y. So x is equal to y squared at the lower limit, and x is equal to y at the upper limit. This is a parabola, x equals y squared. The parabola x equals y squared opens along the x-axis, right? And then this other guy is just the line, y equals x. And then where do the slices live? They live between 0 and 1. You know, what would happen if I crank this up to, say, 2 or something? Okay, so remember what this outer thing says. It tells me where the slices live. And if I'm only interested in this region, then 2 is too far. And I start looking at other stuff, other slices that I'm not interested in. So I don't want to dwell on that right now. I want to just keep it straightforward here for you guys. But that's the effect of changing the range of the slices. All right. What if I want to reverse the order of integration here? So instead of taking horizontal slices, I want to take vertical slices. If you click on this blue integral here, this integrand, you see that I get a pointer? If I click on that thing, it'll reverse the order of integration, dy dx. It turns out that these limits of integration don't make sense if I reverse the order of integration. The ones that are in there for x dx dy don't work for dy dx. And that's something that I mentioned earlier. There's not really any general way of getting from one to the other than just looking at the region and thinking about it. So let's look at this region and think about what would happen with vertical slices. So if we fix an x, we start down here. The slice starts here and ends here, right? So if you're here, what's the y value here? And if you're here, square root of x? Yeah? Okay. So yeah, you have to solve for y in terms of x. Okay, so again, if I pick an x value and I start here, what's the y value for this x? It's just y. And I pick an x value and I go to the top, what's the y value here? It's the square root of x. Sorry. Did I say that wrong? I don't remember what I said now. Anyway, so let's work this out. Oh, and I'm reversing the order of integration there. Okay. So if I fix at x, I start out, what's the y value for fixed x? And then if I go up here, I hope I didn't say that backwards earlier. I think I did. Sorry about that. Okay. So we start at x, we go up to square root of x, and then over what range of x values? Yeah, 0 to 1, so it stays the same. So let's graph this thing. And it's the same thing except I have vertical lines. Okay, so again, I'll say it right just for the record. Pick an x here. Y starts out here at x, and it goes up to root x. Okay. This is a really nice application. Unfortunately, it mixes polar and rectangular. Polar is something we're going to talk about Wednesday. But this is a really nice application because it can actually give you some practice. If you click on this thing, what it'll do is it'll put up little regions down here and ask you to fill out the limits of integration for this particular region. So I just clicked on this guy, and it popped up this region. We see vertical stripes, which means we're integrating with respect to y first and then with respect to x. And the idea is to fill in the limits of integration. So what we have to do is figure out what the equation of this curve is and what the equation of this curve is. And the only way to really figure it out is to infer it kind of from the mouse pointer. So if the mouse pointer is right here, it looks like it's at the point 1, 1. And if I move it up here, it looks like it's at the point 2, 2. So what curve do you think that is? It's just y equals x. And so I start down here at x, y equals x. And then where do I end up? Well, let's see if we can do a little bit of analysis here. If I plug in x equals 1, I get 2. And if I plug in x equals 2, I get 4. So the curve is probably 2x. Okay, and then over what range of values do the slices exist? Looks like x equals 1 here, x equals 2 here. And if I've done it right, if I've done it right, when I hit graph, I should get something that looks similar. Oh, my bad. Thank you. So I haven't done it right. There you go. Okay. And you could think about changing the order of integration on this thing, but that might be problematic. Doing horizontal slices instead of vertical slices. What's problematic about doing horizontal slices here? Yeah, in the vertical direction, I always go from one curve to the other curve. But in the horizontal direction, in here I'm going from this curve to this curve, and then up here I'm going from this curve to this curve. And I don't even know if these guys are horizontal. Like, it might even be there's a bit of a region in there. Right, that's messy. So it turns out that some directions of integration are better than others. And this guy is particularly well suited for a dy dx configuration. That said, it's not an insurmountable problem to go horizontal. How do you think you might handle that? Two integrals. So you can break this thing up into a region here and a region here, and then do horizontal and horizontal here. But it sounds like a lot of work. Okay, so I'm not saying that we're not averse to doing hard work here, but try to make your life easy. Okay, so let's look at another one here. Yeah, so some of them are polar, and I'm just going to skip these for now, but this is something that we'll be talking about on Wednesday. Also polar. Here's an interesting one. The lower curve appears to be what? It appears to be sine, and the upper curve appears to be some constant function. So let's see if we can't figure this one out. So we've got vertical slices, so dx dy or dy dx? Dy dx, because we're integrating parallel to the y-axis first. y starts out at, this does look like the sine function, right? I mean, it's 0. What about here? It's 1. Looks like pi over 2 gives you 1. Pi gives you back to 0. So I believe that this is the sine function. Yeah, we're starting out at sine. And where are we ending up? Well, we got to put it right there. Looks like y equals 2 all the way. Yeah, so y equals 2. And over what range of values do the vertical slices exist? 0 to 2 pi. And I happened to discover in my office this morning that it understands the word pi, which is convenient. Yay. Horizontal slices? Not so much. Yeah, it would be pretty gross. So horizontal slices, let's see, you would have to do from here to here, maybe up to here. And then you could do this whole top piece pretty easily. And then you would have to go from here to here, and then down here from here to here. So it's like 3 or 4 integrals. Yeah, it's a lot of work. Vertical slices. Okay. Yeah, I got time for one more example. Possibly 2. So I'm going to go to the book now. So I encourage you guys to go home and play with this thing. Maybe do some of the practice problems. Don't worry about the polar ones, but think about some of the, man, there are a lot of polar. There's a rectangular one, rectangular, polar, polar, rectangular. So you get the idea. Just try some of the rectangular ones. Okay, 15, yes, 15. Compute that integral. I'm not so much interested in computing it right now as I am understanding what the region of integration is. Vertical slices, integrating with respect to y first. That means you're going from y equals this up to y equals this. Let's just focus on the top thing here. Y equals that. What kind of curve is that? Let me write it out for you. It's that, right? Not a circle. It's the upper half of an ellipse. In fact, this guy, once I squared it, became the whole ellipse. How do you figure out what that ellipse looks like? The easiest way to, I just know that that's an ellipse, and then the way I figure it out is if x is equal to 0, what's y? Yeah, and if y is equal to 0, what's x? Plus or minus 1 over root 2? Plus or minus root 2 over 2 if you want to rationalize the denominator. So that's, I don't even know, like here-ish. Okay. So it's that ellipse. Let's go back and look here. I'm going from the bottom of the ellipse to the top of the ellipse in the y, along the y direction. That's like that, right? And over what range do these slices exist? From 0 to root 2 over 2. So that corresponds to what part of the ellipse? The right half. Exactly right. The right half. That's the region of integration for that guy. Do you think you could reverse the order of integration if you worked hard? Yeah, wouldn't be too bad. You could do that. In fact, it would be something worth trying. It might be that reversing the order of integration I'm not saying that it's for sure, because I haven't done the problem. But it might be that reversing the order of integration would help, because if you reverse the order of integration here, you're still going to get square roots, right? You're going to get square roots of like 1 minus y's or something, y squared. But when you integrate with respect to x first, what's this turn into? It turns into 1/2 x squared, and that x squared, when you start shoving square roots into it, nice things are going to happen. Right, so it might be, I'm not saying that it is, but it might be easier to do this by reversing the order of integration. That's the kind of stuff that you want to think about when you're doing that stuff. Let's talk briefly about 18, and then I'll let you go. The volume bounded by the paraboloid and the plane z equals 4. Paraboloid, right? Z equals 4, right? So z equals 4, the plane is truncating the paraboloid. And I'm not interested now in the volume below the paraboloid. I'm actually interested in the volume between the paraboloid and the plane, which in a way is much more reasonable thing to think about than the other thing that we were talking about. How do I find that volume using an integral? And think, before you answer, think about area between curves. Do you remember how to find the area between curves back in Calc 2?
Well, could you just take the volume of the cylinder and then do the same method for the lower part, just subtract?
You absolutely could. Right. So it's basically that idea, but we can generalize it to something more along the lines of what Ethan was saying. When you were finding the area between curves f and g, you took the top curve minus the bottom curve, and you integrated across. The exact same thing holds here. Take the top surface minus the bottom surface, and you get the volume between the two. So that's why I wanted to briefly point that out before you got to it this evening or tomorrow. Any last questions? Got to do a lot of these problems, people. All right, see you on Wednesday.